Today's lesson is on inequalities in triangles. This is our last lesson in this wonderful unit on relationships within triangles. So here we go. We're going to first talk about a comparison property of inequality, and it says if A equals B plus C and C is greater than 0, then we know that A has to be greater than B, right? That almost makes so much sense. It feels like you don't even need to say it. But it is a property, and so we write it down. And of course, we know that A would have to be greater than C as well, right? So we're going to kind of use that when we start to look at this corollary here. You remember the triangle exterior inequality theorem? It was like this. Triangle exterior angle theorem said this. The measure of angle 1 equals the measure of angle 2 plus the measure of angle 3, right? You remember that? We had that last unit or maybe the one before that. Well, now the corollary to that says the measure of the exterior angle of a triangle is greater than the measure of each of its remote interior angles. And again, like the inequality property above, of course, that makes perfect sense. Because if the measure of angle 1 is the sum of these two measures, then clearly the measure of angle 1 has to be greater than the measure of either one of those angles by itself. And that's all that corollary says. So that leads us into this theorem, 5-10, that says if two sides of a triangle are not congruent, then the larger angle lies opposite the longer side. So let's say that we've got xz here, xz right there, and xy. So those aren't congruent because they're telling us that this is longer and this is shorter. That's an S. So longer, shorter. All right. So if that's the case, then I know that the larger angle has to be across from the longer side. So therefore, the measure of angle y, which is right here, has to be larger than the measure of angle z, which is right here, z because it's across from the shorter side. Okay, that's it. So let's see if we can put that into practice here. A town park is triangular. Wonderful. Triangular parks. See them all over the place. The landscape architect wants to place a bench at the corner with the largest angle. How is he going to decide which corner that'll be? Well, we're just going to use that theorem that we just learned, and we're going to say, okay, well, I know the largest angle has to be across from the longest side of that triangle, which tells me that the bench is going to have to go in between which two streets? So it would be MLK Boulevard and Valley Road, right? Because that's the longest side, this is the medium side, and this is the shorter side. If I wanted to put it at the corner that has the smallest angle, then I would put it at the intersection of Hollingsworth and Valley Road, but that's not what we want. We want it at the largest angle, and so that's how we use that theorem. Okay, let's have another theorem. It says if two angles of a triangle are not congruent, then the longer side lies opposite the larger angle. All right, well, it's kind of just the opposite. We switch the sides and the angles in the theorem that we just had. So if two angles of a triangle are not congruent, so we got angle A here that we can see its measure is larger than the angle at B, that's what we got, then we know the longest side, the longer side, is across from the larger angle. So that means BC is going to be longer than AC, which is going to be shorter. Makes sense, makes perfect sense. Okay, so here's an example for us. List the sides of the triangle TUV in order from least to greatest. Well, the first thing we need to do, since we don't know any side lengths, is we need to figure out what all the angle measures are. And let's see, so we got 58 and 62, that's 120, which means this angle here measures 60 degrees. All right, so 62 is the largest of the angles, so that's going to be my long side. 60 is in the middle, that's going to be my medium side. And TV then is going to be the shortest side in that triangle. So and I got to be careful here, when I have a test or a quiz, I got to be sure I put them in the correct order, least to greatest. So the shortest side is going to be TV, next is going to be UV, and next is going to be TU. All right, if I wanted to write that as an inequality, I would do it this way. I would say TV is shorter than UV, which is shorter than TU. That's another way, but remember, if you're using inequalities, we don't want the bars over the top of our letters because we're talking about lengths if we're using inequalities. All right? Here comes another theorem, triangle inequality theorem. The sum of the lengths of any two sides of a triangle is greater than the length of the third side. Okay, so I got a triangle. Let's look at it. The sum of the lengths of any two sides, so let's call this side A, B, C. All right, so what do I know? Well, the sum of the lengths of any two sides, so let's pick A and B first. I know that has to be greater than the length of the third side. Okay, let's do A plus C. I know A plus C has to be greater than B, and I know B plus C has to be greater than the other side length, and that's all this is telling us here. All right, I thought it might just be a little bit easier if we didn't have so many X's and Y's there, but the sum of the lengths of any two sides of a triangle is greater than the length of the third side. So let's see how that's going to play out if we put some numbers up here. Okay, can a triangle have the sides given below? Let's see, so is 3 plus 7 greater than 8? Yes, it sure is. And of course 3 plus 8 is greater than 7, and 7 plus 8 is greater than 3. So yes, for sure, we can have that. Okay, right away I can see that this one's going to be a no. How come? Because 5 plus 10 is not greater than 15. 5 plus 10 equals 15. So therefore I could not make a triangle with those side lengths. Okay, here's another example for us. Triangular sandbox. That's interesting. Probably, I doubt I've ever seen a triangular sandbox, but I'm about to draw one for you. Okay, so let's see. We got side lengths of 5 feet. We got one that's 8 feet, a little bit longer, and we want to know what's the range. What's the range of possible lengths for that third side? Okay, well here's what we know. We know that x plus 5 has to be greater than 8, right? So that tells me x has to be greater than 3. And I also know that 5 plus 8 has to be greater than x. So 13 has to be greater than x. And of course, I could look at this, right? X plus 8 has to be greater than 5, but I really don't have to write that one, right? Because 8 is greater than 5, so that one doesn't really have to be done. So let's write this as a compound inequality, x in the middle. So from right here, I know that x has to be greater than 3. And from right here, I know that x has to be less than 13. And of course, I want to put my units on there. So that side, to make that sandbox, could be anywhere from just a little greater than 3 to just a little less than 13. All right, so that's how you're going to do a problem like that. Okay, we got 3 problems here. Let me do one, and then I'll pause, like I like to do, and I'll let you do the other ones, the other 2. For each of the triangles below, how come I know the measure of angle 1 is greater than the measure of angle 2? Okay, well, let's think about this. All right. So, let's see. I know, okay, so if I use the corollary that I learned today, so I'll write this. It says explain it. By the triangle remote exterior angle corollary, I'm going to abbreviate that, COR, I know that the measure of angle 1 is greater than the measure of angle 3, right? It's also greater than the measure of angle 4, but 4 is not really related to angle 2, so I'm going to pick this. All right, so how does that help me? I hope you're thinking, oh, by the vertical angles theorem, angle 2 is congruent to angle 3. Therefore, I know that the measure of angle 1 has to be greater than the measure of angle 2. Now, of course, if I were doing a proof, I would have to change this congruent statement to an equality, and I would have to use substitution, but luckily I'm not doing a proof, so that will suffice. Angle 2 is congruent to angle 3. The measure of angle 1 is greater than the measure of angle 3. Therefore, I know that the measure of angle 1 has to be greater than the measure of angle 2. Okay, I want you to pause right here, and I want you to write down these explanations. Okay, so on number 7 here, all we have to do is apply the corollary, right? Because I've got this triangle right here. Angle 1 is a remote exterior angle, so by that corollary we learned today, I know that the measure of angle 1 is greater than the measure of angle 2 and greater than the measure of angle 4, so I don't even have to apply any logic there. Okay, how about number 8? Well, I have to notice that these two lines here are parallel, okay, and so that tells me that angle 2 here is congruent to angle 4. By the triangle remote exterior angle corollary, I know that the measure of angle 1 is greater than the measure of angle 4. Also, it's greater than the measure of angle 3, but I don't really need angle 3 in this problem. And since angle 4 and angle 2 are congruent by the alternate interior angles theorem, I know that the measure of angle 1 has to be greater than the measure of angle 2. If you didn't get that just right, then please get that noted in your paper. All right, now that was inequalities in one triangle. Now we're going to switch over and talk about inequalities in two triangles. These were really two separate lessons in your book, but I decided to combine them into one fabulous video. Okay, so here we go, the Hinge theorem. The Hinge theorem says if two sides of one triangle are congruent to two sides of another triangle and the included angles are not congruent, then the longer third side is opposite the larger included angle. So look at this picture here. AB, wait, if it says the included angles are not congruent, okay, so they're telling us the measure of angle A is greater than the measure of angle X, and you can see how they've got them drawn so that A looks bigger than X. If that's the case, and I've got two congruent sides in each of those triangles, then I know that the longer side has to be across from the larger angle. So BC is greater than YZ. So longer, shorter. That's all the Hinge theorem tells us. Okay, and then of course, the Hinge theorem has a converse. And it says if two sides of one triangle are congruent to two sides of another triangle, and the third sides are not congruent, so in this case they're telling us that BC is longer than YZ, then I know that angle A has to be the larger angle because it's across from the longer side. Okay, so longer, shorter, and this will be, that just means angle A has to be greater. Okay, Hinge theorem and its converse. So I think the rest of our lesson is going to be putting those two things into practice. Okay, write an inequality relating sides SK. So here's SK, and here's YU. And before I can do that, I got to make sure that I have the requirements of the Hinge theorem or its converse fulfilled, which means I got to have two congruent sides. So that one and that one, I got it. Okay, so I got to look at the included angles. Angle A is greater, the measure of angle A is greater than the measure of angle O. Therefore, by the Hinge theorem, SK has to be longer than YU. That's it. Not too bad. What do we got next? In triangle ABC, A, B, C, let's see, AB is 3, BC is 4, CA is 6. In triangle PQR, PQ is 3, QR is 5, and RP is 6. So let's mark what I have that's congruent here. Congruent, these two are congruent. All right, so I'm going to highlight the sides that are not the same length. I got that one, which is 5. I got this one, which is 4. So use an indirect proof. Ooh, an indirect proof. Okay, so I know that the measure of angle P is greater because QR is greater than BC, but I need to use an indirect proof. So let's remember what we got to do with an indirect proof. We got to assume the opposite of what we're trying to prove. So we're going to assume that the measure of angle A is greater than the measure of angle P. That's the opposite of what I'm trying to prove, right? And I know that by the converse of the Hinge theorem, if the measure of angle A is greater than the measure of angle P, then I know that BC is longer than QR, right? That's what that would tell me. But it's given that BC isn't longer. So I'm going to say it this way. But it is given. Well, let me do this. I'm going to say, but this contradicts, because remember, in an indirect proof, I'm always trying to find a contradiction to prove what I'm trying to do. But this contradicts the given information, which is that BC is shorter than QR. Therefore, the measure, therefore our assumption is wrong, and the measure of angle P has to be greater than the measure of angle A. Now, of course, your indirect proof might state things a little bit differently. You might say our assumption is impossible, or it is impossible for our assumption to have been correct. You know, it's words. As long as you back up your words with something that's mathematically sound, you're going to be okay. All right, what do we have next? What is the range of possible side lengths? Let's see where I am in my notes. What is the range of possible values for the variable? Oh, okay. All right, well, let's see what we got here. We got this congruent to this, and of course we know this is congruent to itself, so we got to look at these included angles here. We got 28, and this one here is 2y minus 7. Okay, 2y minus 7, the side across from it is 11, the side across from 28 is 12, so we know that 28 is the larger one. right? So what are we going to do here? Okay, we know that this angle that I've got highlighted here is larger than the one that's 2y minus 7. So what I'm going to say is 2y minus 7 is less than 28, right? Isn't that what we just said? 2y minus 7 is less than 28. But I need a range. That's not going to give me a range. That's going to give me a number. So what I know is that this angle here, 2y minus 7, it's got to be greater than 0. So you got to have that greater than 0 on the left side. So now we're going to solve this, both sides, add 7, add 7. So we'll have 7 is less than 2y, it's less than 35. Divide everything by 2, and I'm going to get 7 halves is less than y is less than 35 halves. And that is your answer right there. You got to have a range. Y's got to be greater than 7 halves. It's got to be less than 35 halves. Okay, why don't you pause and do number 14 by yourself and then come back and check. Okay, look at number 14 there. Is that what you got? I did it just like I did the previous one, noting that 15 is longer than 14, which means that 50 degrees is larger. Right here, 50 degrees has to be larger than the 4x minus 10 angle. Then I set up my inequality, solved it, and got the answer you see there. Put a star here or a note if you need us to talk about this further in class. Okay, here's another one. Good problem. A quilter cuts out and sews together two triangles, like we see right here. She tries to make triangle ABD and BDC equilateral, but you know, she's only human, so it didn't come out perfectly. The angle measures are shown. Assuming that side BD is actually the same in both triangles, which segment is the longest side in the figure? All right, well, I'm going to start. When I have a problem like this, I like to label both triangles. So let's look at the left triangle, ABD, and figure out the side lengths in there. I know that this is going to be the longest side, right, because 61 is the largest angle. This will be the medium side, and this will be the shortest in the left triangle. Okay, now I'm going to label the right triangle. I know that BD is the longest side in triangle BDC. I know that this is the shortest side, and BC is the medium length side in that triangle. If you need to pause here and take a minute to let that soak in, then go ahead and do that. Okay, so out of all this, I'm looking for the longest side in the figure. Okay, so here's the way I think about this. BD, look at BD here, guys. It's the shortest side in the left triangle, but it's the longest side in the right triangle. So I know that BC, let me write myself a note, BC is shorter than BD, and CD is shorter than BD. But in the other triangle, these other two sides are both longer than BD. Right? Those are AB and AD are longer than BD, so I know that they're longer than BC and DC. You may have to pause and think about this. So what I know is that AD, this one right here, has to be the longest side in the whole thing. You might have to think about that a bit, and if you need to, we'll do another problem or two like this one in class next time. Okay? You might have to pause and give that one some thought. I like that problem. Hint, hint. Okay, now we got a proof. All right, I'm going to pause and set up my two columns, and then I'll come back. And so this video is already getting long. I don't want to make it any longer than necessary. Okay, so right away, when I look at what I'm trying to prove, I feel like, okay, I'm going to probably need to use the Hinge theorem to do that, right? So remember, I always like to kind of figure out where I'm going and then fill in the middle steps. Well, let's just start with C being the midpoint of BD. What does that tell us? It tells us that BC is congruent to DC. They wouldn't give us that information if we didn't need it. And I know that's the definition of midpoint, right? Okay, then they tell us that the measure of EAC, this angle right here, equals the measure of AEC, this one right here. So I'm trying to set up the hinge theorem, so what I need is another set of sides in those two triangles that are congruent. So I think what I got to do right here is I got to turn this into a congruent statement. So I'm going to say angle EAC is congruent to angle AEC, and that's the definition of congruence, right? And then, how does that help me? Oh, because then I can say that AC is congruent to EC, and how is it I know that? Oh, it's the converse of the base angles theorem. Base angles theorem converse, right? Base angles theorem converse. Okay, so now everything's all set up. I've got two sides of two sides of one triangle congruent to two sides of another triangle, and then this statement here that they gave me told me that one of the angles is larger than the other one. Therefore, I'm able to say that AB, since it's across from the larger angle, is greater than ED, which is opposite the smaller angle, and that's exactly what the hinge theorem says. So that's how you would use the hinge theorem in a proof. That's a beautiful, simple little proof. That's it. Please keep studying your flashcards, and we'll see you next time.